Now let's take a look at example number 3. In this example, we're going to be asked to use the graph that's given below, which is a graph of the function f of x. Okay? We don't know its formula, but we're just told that this is the graph of the function f of x. And what we want to try to do is, down here, you can see that I've set up some axes that are fairly similar proportion-wise to the ones that I have up above. And I want to use that set of axes to create a rough graph of what f prime of x looks like. So what's interesting here is that in example number 2 that we just completed in the last video, we were given a function of f, and we were able to find a formula for f prime. But now I believe that it's possible to at least get a rough graph of f prime if I only had the graph of f itself. And the way that I understand how to do this is by keeping in mind the relationship between the function f of x and the function f prime. Now, that relationship again is that, remember, the derivative represents or calculates the slopes of tangent lines on the original graph. So let's go ahead and take a look here at some of the things that we can state about the graph that we actually have right here, and see if we can use this to try to create a table of values that are going to be x values and slopes of tangent lines. These pairs are going to correspond to points on the derivative. Let's take a look at some examples to kind of see how this would work. Okay, so on this picture here, I can go ahead and I can pick a whole bunch of different points, and I might be able to go ahead and select that at some different points, I can draw some tangent lines and find their slope. So let's say, for the sake of argument, we start maybe here at this value of around 1. Okay, if I was to go up to the top, or to go up to the point on the function f, if I was to draw a tangent line here, I might be able to see that this tangent line might look something kind of like this. Okay, now if I had to take a guess about the slope value of this particular tangent line, any idea what we might say the slope of that blue line is? I mean, it does look pretty flat, right? Okay, well, if the slope does look pretty flat, then we might be able to say that this has a slope of roughly 0. So what this means is that we have found that if I was to take the x value of 1 and try to think about what the derivative function would spit out, remember the derivative should be always telling me the slope of the tangent line at a particular point. It should be telling me 0. So what this means is that on the graph of my derivative, I should have a point 1, 0. This is a point on my derivative graph, and so I'm going to go ahead and sketch this out in blue. Now notice I could probably go up to this original function f of x and continue to do this. And in fact, finding times when the derivative is going to spit out 0 is probably some of the easiest stuff to start looking for, because it might not be too much work to find when I'm going to have a slope of 0. Notice that it looks like maybe somewhere around here, I might also get something like a slope of 0. Well, let's go up here and say, I don't know, maybe this is like at, say, 3.7. I'm just eyeballing it right now. Again, I'm looking for a rough graph. But at this point, it looks like, again, I'm going to get a horizontal tangent line that is slope 0. So I could say the slope 0 is obtained, at least roughly, say when I plug in a number like 3.7. So if I was to follow this down on this graph, let's say about 3.7 is right here, I know that I should have, again, the point 3.7, 0 in this picture. Okay, are there any other spots on here where I might get a slope of 0? Well, yeah, maybe over here I could imagine I could draw out a tangent line. That would have slope 0. But of course, I might need to ask the question, where exactly is this value? If -1 is around here, then maybe this is around, say, -0.5. Okay, so maybe over here on the graph, again coming down, maybe this is about -0.5. I would have -0.5, 0 again as a point on this curve. So there's another dot. Okay, so you can see how I can slowly start to kind of fill in some different points that are going to be on this graph. Now we've pretty much taken care of all the easiest points, but I'm going to show you how we can start to take a look at some other points that are going to be on the graph. They're a little bit more complicated, but not too bad. Let's suppose, for the sake of argument, that we were going to look over here at, say, a value of 2. Okay? So let's suppose that we're going to do that. We're going to look at the value of 2 right here and think about the slope of the tangent line. Now, I don't know exactly what the slope here is. I might not even know roughly how to approximate it. But I definitely can tell you that here, for this tangent line, the slope is certainly negative, right? Like, we know that it's a negative amount of slope. And it might be fairly steep. So what I can say here is that there is definitely going to be some value over here. Maybe I'll just write it as some negative number. So even though I don't know exactly what the slope is, I know that at the value of 2, which is maybe going to be in here, I'm going to get some value that's negative. Again, I'm just providing a rough sketch, so this is totally okay. Notice at the value of 3, I'm going to get something that's negative. And I can start to see that there's a general trend of tangent lines in here. Notice that tangent lines that are close to 1 are going to have not as steep, not as negative of slopes. Maybe a slope of like -1 versus -3 or something like that. And then the slopes get more and more and more and more and more negative. They get really negative, but then notice that slopes down here start to kind of level out. They become less negative as I approach maybe that point around 3.7. So notice that that would mean that I'm going to get numbers that are negative, more negative, more negative, less negative, back to 0. If I thought about drawing this in a picture, I could imagine that I would have y values that go more negative, more negative, more negative, more negative, but then slowly have to start becoming less negative and going back to 0. So here's kind of what the graph of the derivative would look like. Notice I could do the same sort of analysis after 3.7. Notice over here, tangent line slopes are going to be positive. So maybe around the value of 4, I can state that I am going to have some positive number for my slope. And actually, every tangent line after that fact is only going to continue to get steeper and steeper, a bigger positive number. So after this, I'm going to get some positive y value, then a bigger positive y, then a bigger positive y, and then a bigger positive y. This is just going to keep going up, 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 up. Notice over here, between -0.5 and 1, I'm going to have slopes that are going to be positive, more positive, and then slightly less positive. So I'm going to have slopes that are more positive, less positive, less positive. And I'm kind of connecting between these dots. Before -0.5, maybe around -1, I can see that I'm going to have slopes that are negative. And before that, I had slopes that were even more negative, and then more negative, right? So super negative, not as negative, 0. Well, that would give me a picture like really negative, less negative, less negative, less negative, less negative, and finally 0. So this right here might be a graph of f prime of x. So you can kind of see again that this is a slightly weird process in that we're taking a look again at the slopes of the tangent lines on the original graph, and those end up being the y values or the outputs of the f prime function. Now this process may take a little bit of time to get used to, but it's actually not too terribly difficult to go ahead and try to repeat with even just a wide variety of functions. You could almost just go to a page and sketch out any function that you know. Maybe sketch out something like y equals x squared. And you could try to repeat the same process and then actually calculate the derivative and see if your picture roughly matches up with the actual function that you would have calculated. So go ahead, maybe give that stuff a try, take a look at some problems in this corresponding worksheets, and we'll see that in the next video we'll continue to tackle some questions like this as well.